Hey, welcome to ezLecture. I'm your host, Professor Ashley Carter from Amherst College's Physics Department. We've got a great series of lectures planned for you on physics and math concepts. Let's get started.
Today's lesson is on working and deriving in different coordinate systems.
Many times in physics, we want to understand the motion of objects that move in a circle, objects that are in rotating frames, or objects that are confined in some way. In these instances, it might be harder to find this motion in the Cartesian coordinate system. And it might be a lot easier to define the motion in a different coordinate system. The trade-off is that in this non-Cartesian coordinate system, we'll have to be very careful when calculating derivatives or integrals, complicating calculations of motion or work.
For example, say we want to describe the circular motion of a ball being swung on a string. Instead of using Cartesian coordinates, let's say that we want to use a radial coordinate r and an angular coordinate phi. R will describe the distance of the ball from the origin, and our angular coordinate phi will describe the angle that's swept out by the ball. Now let's say we want to calculate the velocity of the ball. If we were going to use Cartesian coordinates, the velocity would just be the derivative of x times x hat plus the derivative of y times y hat. Simple enough. But remember, we want to use the radial coordinate and the angular coordinate. Some students think that the velocity then should be the derivative of the radius times r hat plus the derivative of phi times phi hat. But this is actually incorrect. You can tell it's incorrect just by looking at unit analysis, because the units of the velocity should be length per time, not angle per time. The velocity should actually be the derivative of the radius times r hat plus the derivative of the angle times r phi hat. There's this funny extra r in the angular term. This angular term is actually the tangential velocity, and you probably remember it as r omega. It's coming back to you now, and you probably really didn't think anything of it at the time. But now that I've compared it to the velocity in Cartesian coordinates, it looks a little funny. Our goal in this lesson is to show you why this derivative has this extra r in it, and to introduce you to working and deriving in different coordinate systems.
At the end of this lesson, we want you to be able to read the notation for a non-Cartesian coordinate system and be able to find a derivative or a spatial integral. Knowing how to do these things will enable you to find the physical quantities of displacement, velocity, acceleration, work, center of mass, or moment of inertia.
Our learning goals for the lesson will be to, first, define the displacement vector in non-Cartesian coordinate systems. These are polar coordinates, spherical polar coordinates, and cylindrical polar coordinates. We also want to calculate time derivatives in these non-Cartesian coordinate systems. And finally, we're going to calculate spatial integrals in these non-Cartesian coordinate systems. We'll be using a text of reference of Classical Mechanics by Taylor. Polar coordinates are listed on page 26 and 34. Cylindrical polar coordinates are on 34 and 40, and spherical polar coordinates are on page 135. So they're sort of scattered throughout the book, and you should be referring to these pages for help while we do this lesson. Our first goal is to define the displacement vector. We'll start by defining the displacement vector in Cartesian coordinates. Every coordinate system needs to uniquely identify a point, say P. In Cartesian coordinates, you have three coordinates: x, the distance along the x-axis, y, the distance along the y-axis, and z, the distance along the z-axis. The displacement vector is the vector between the origin and our point P. This vector can be written in two ways. The first way is to write it in terms of the unit vectors of the system. These unit vectors are x hat, y hat, and z hat, which are along the x, y, and z axes. Sometimes books will write these vectors as I hat, j hat, and k hat, but we'll stick with the book's notation of x hat, y hat, and z hat. These unit vectors have a couple of interesting properties. First, they define our coordinate system. Second, they are always unit vectors, so they always have a magnitude of 1. And third, they're always perpendicular to one another. To define the vector in terms of the unit vectors, we need to write down the magnitude of the vector along each direction defined by the unit vectors. For example, in Cartesian coordinates, we write down x hat plus y hat plus z hat. The second way to write the vector is by using parenthetical notation. Here we just put the parentheses and then we write our components x, y, z. The magnitude of our displacement vector, little r, is given by the Pythagorean theorem in Cartesian coordinates, such that it is square root of x squared plus y squared plus z squared. Having now defined this displacement vector, let's stop and do an exercise to make sure that you have it. The problem that we're going to do is we're going to write down the displacement vector in terms of both the unit vectors and the parenthetical notation using the Cartesian coordinates. And then I want you to calculate the magnitude. Here I've got a graph. You can see this is the x-axis and the y-axis, and I've located the point P for you. Go ahead and write down the displacement vector in terms of these unit vectors and the parenthetical notation. To answer this question, you should have written 3x hat plus 4y hat for the displacement vector in terms of the unit vectors. In parenthetical notation, you should have just written 3, 4. The magnitude of the displacement vector is just going to be 5. This problem was a little bit easy, but we're going to define the displacement vector in a couple of non-Cartesian coordinate systems, and so it's going to get a little bit tougher. Let's go ahead and define the displacement vector using polar coordinates. Polar coordinates are useful when the problem has circular symmetry. Here's the 2D polar coordinates. The first coordinate is r, which is the distance from the origin to the point. And the second coordinate is phi, which is the azimuthal angle defined as the angle from the x-axis. Math and physics differ on the symbol for these coordinates, and even within physics, different books will tell you different symbols. What we're going to do is we're going to use the symbols that Taylor uses in his book. These symbols are r for the radial distance and phi for the azimuthal angle. R is a really good choice for this radial distance because we've already defined the distance from the origin to the point as the displacement vector, and we've said that its magnitude is r already. So we don't have to change that definition if we use r. The parenthetical notation for the displacement vector is easy. It's just going to be r, phi. Writing the displacement vector in terms of unit vectors is a lot more problematic. What we need to do is we need to first define the directions for these unit vectors, r hat and phi hat, and then define the coordinates r and phi. R hat and phi hat are going to be unit vectors that look like the following. R hat is going to point along the radial direction outward, and phi hat is going to point counterclockwise from the x-axis. Of course, r hat and phi hat must be perpendicular to one another, so I've drawn them as perpendicular vectors here. To define these vectors, we're going to need to define x and y in r and phi. X and y are going to be x equals r cosine phi and y equals r sine phi. What we can do is we can then invert these to find r and phi, And r is just going to be given by the Pythagorean theorem. Phi is going to be the inverse tangent of y over x. You should make sure that you know how to derive all 4 of these coordinates. To find r hat, all we do is we take the displacement vector and set it over the magnitude. This will give us a vector in the correct direction, and it will have a magnitude of 1. Since we know in Cartesian coordinates that it should be xx hat plus yy hat, we just make that substitution. And now, since we know that x and y in terms of r and phi, we'll plug that in as well. You can see that this r drops out, and we suddenly just have cosine phi x hat plus sine phi y hat. Now this may be a little strange, because it means that this unit vector depends not only on x hat and y hat, but it also depends on phi. That means if a point's phi changes, the unit vector also changes. This is a little odd, because you're used to having x hat and y hat always being stationary, they never move. R hat is going to move with the point. Now let's go ahead and find phi hat. We know phi hat is going to have a component along the x hat direction, and we'll call that phi x, and it's going to have a component along the y hat direction, and we'll call that phi y. What we want to do is figure out what those components are. The other thing that we know is that we know that it must have a dot product with r hat of 0 because these are perpendicular to one another. So what we're going to do is we're just going to plug in what we already know for r hat and phi hat. So we've got our expression for r hat dotted with phi hat. Simplifying, we get phi x times cosine phi plus phi y times sine phi is going to be equal to 0. And just by inspection, we can tell what phi x and phi y must be because we know it has to equal 0. A good guess would be negative sine phi x hat plus cosine phi y hat. And this guess will get us a unit vector that points in the counterclockwise direction from the x-axis. Alright, now that we've defined the polar coordinates and their unit vectors, we can go back to this business of defining the displacement vector and polar coordinates. To define the displacement vector, we first note that the displacement vector in Cartesian coordinates is xx hat plus yy hat. We're just going to plug in our expressions for x, r cosine phi, and our expression for y, r sine phi, into this equation. And what we notice right away is if we factor out the r, this expression cosine phi x hat plus sine phi y hat is really r hat. So our displacement vector in terms of unit vectors is r hat. And this makes sense because remember, all we need to in order to define a vector is the magnitude, which happens to be r, and the direction, which happens to be r hat. Or does it make sense? Remember when we wrote the parenthetical notation, it was r comma phi, but it doesn't seem like there's any phi in this equation. We know that the incorrect version is r hat plus phi hat, and the correct version is r hat, but it just seems weird that there's not a phi in this correct version. Why is the incorrect version incorrect? Where did the phi go in our correct version of the displacement vector? Take a moment and think about the answer.
First, let's answer the question of where did the phi go in our correct version of the displacement vector. The answer is that the phi is already present in the form of r hat. R hat depends on phi explicitly, so phi is in the equation even if you can't see it. This is very different from the Cartesian unit vectors, which are fixed in place and don't depend on any variables. Now let's answer why the incorrect notation is incorrect. If we were to add an extra phi hat term to the displacement vector, then of course you'd be adding another component to the correct vector. A component, might I add, with the wrong units. But I can see why students get confused. In the parenthetical notation for polar coordinates, you write down both the r and the phi. You just don't do this when expressing the vector in terms of the unit vectors. Remember, I said that these two notations were not equivalent, and now you can see why. The unit vectors actually have a larger role than just denoting that this term or that term is the radial term or the angular term. Don't dismiss these unit vectors or you'll get into trouble. Now that we've defined the displacement vector and polar coordinates, let's try some exercises using what you have learned.
Okay, let's do the same problem that we did before, except this time let's use polar coordinates. So again, I want you to write down the displacement vector in both the parenthetical notation and in terms of the unit vectors, but this time I want you to use polar coordinates. And again, also calculate the magnitude. Go ahead. You should have found the radial coordinate r to be 5, and you should have found phi to be the tan inverse of 4 over 3, which is just y over x. For the displacement vector, you can write the displacement vector as either 5r hat in the unit vector notation, or as 5 comma tan inverse of 4 over 3 in the parenthetical notation. Let's do another problem. In this problem, we're going to be given the expressions for x and y. I want you to write down the displacement vector in terms of the unit vectors for both the Cartesian and polar coordinates, and then I want you to tell me which expression is simpler. In Cartesian coordinates, remember, we're just going to write x hat plus y hat. So we'll just plug in the expressions for x and y. In polar coordinates, it's a little more difficult because we need to find the magnitude r. R is just going to be t sine 2t squared plus t cosine 2t squared, square root of the whole thing, and that just is t. Therefore, the displacement vector is just going to be t r hat. And you can see that this expression here is a lot simpler than the expression in Cartesian coordinates.
There are still two more coordinate systems that we need to discuss: cylindrical polar coordinates and spherical polar coordinates. Both of these 3D systems are based on the 2D polar coordinates.
Let's go ahead and define the displacement vector in cylindrical polar coordinates. In cylindrical polar coordinates, we're going to define the point P by 3 coordinates. The first coordinate is the radial distance along the x and y axis. The second is the azimuthal angle from the x-axis, and the third is the coordinate along the z-axis. There's different values that these coordinates can take, but we're going to use the notation that's in your book. We're going to use rho for the distance along the radial distance along the x and y axis. We're going to use phi as the azimuthal angle, and we're going to use z as the distance along the z-axis. The best time to use this coordinate system is on objects with cylindrical symmetry. That's because you can use rho and phi to sort of describe the circular symmetry, and then you can use z to describe the long axis of the cylinder. Let's go ahead and define the two ways to define the displacement vector. The first way is using parenthetical notation, and we'll just define it as rho, comma, phi, comma, z. The second way, we want to use the unit vectors, but let's first go ahead and define these unit vectors. The unit vectors are going to be rho hat, which will just point along the radial distance in the x and y plane. We'll have phi hat, which will point counterclockwise in the x and y plane from the x-axis. And then we'll have z hat, which will point along the z-axis. Rho hat is sort of similar to our r hat in polar coordinates. And here you can see it has the exact same formula. Phi hat is going to be exactly the same as phi hat in polar coordinates, and it has the same formula. And z hat, of course, is just z hat. You can see from this definition that we're really mixing the best of polar coordinates with Cartesian coordinates. Let's go ahead and keep defining the displacement vector in terms of these unit vectors. To do that, we're going to have to define our coordinates. X is just going to be rho cosine phi, y is rho sine phi, and z is z. If we invert these coordinates, we'll find that rho is just equal to the square root of x squared plus y squared via the Pythagorean theorem. Phi again is just going to be the tan inverse of y over x, and z will equal z. To define the displacement vector, we're just going to take our Cartesian vector, xx hat plus yy hat plus zz hat, and we're going to plug in the x, y, and z coordinates. Collecting the terms, we can see that this cosine phi x hat plus sine phi y hat is really rho hat. And so this displacement vector is going to simplify to rho hat plus zz hat. Again, that we see that phi does not explicitly appear in our definition for the displacement vector, but phi is inherently a part of rho hat. So rho hat, just like the polar vector r hat, does depend on phi. Let's do some problems in this coordinate system to make sure that you are able to define the displacement vector. For the first problem, we've located the point P here in our 3D coordinate system. I want you to write down the displacement vector in both the Cartesian and cylindrical polar coordinates and find the magnitude of that displacement. For Cartesian coordinates, you should have found that the displacement vector in parenthetical notation is 3, 4, 12. In terms of unit vector notation, it should be 3x hat plus 4y hat plus 12z hat. But for cylindrical polar coordinates, you should have gotten 5, tan inverse 4 over 3, 12. And in unit vector notation, you should have gotten 5 rho hat plus 12z hat. The magnitude of r, of course, for both of these systems is going to be 13. Hopefully this was an easy problem, so let's try another one. In this problem, I give you expressions below for x, y, and z, and I want you to write down the displacement vector in both the parenthetical notation and in terms of the unit vectors for cylindrical polar coordinates. You should have found that the displacement vector has the following parenthetical notation. Rho, of course, is just going to be t. Phi is going to be tan inverse of cotangent of 2t, and z is going to equal t. In unit vector notation, we'll have t times rho hat plus t times z hat. Finally, let's define the displacement vector in spherical polar coordinates. Now let's define the displacement vector. The displacement vector in parenthetical notation is going to be r, theta, phi. Notice that our colatitude, theta, is listed before the azimuthal angle phi. This is incredibly confusing because in cylindrical polar coordinates, or polar coordinates, the azimuthal angle is listed second. In addition, in math, the azimuthal angle is listed second too, not third like it is here. So you'll have to be very, very wary that this colatitude is listed second here for our notational purposes. The reason why we physicists choose to write the notation this way is actually that theta is the polar angle in spherical polar coordinates, not phi. If you look at the graph, you can see that z is the projection of the radial coordinate r onto the z-axis. So z equals r cosine theta. And the cylindrical coordinate rho is the projection of the radial coordinate onto the xy plane, which is equal to r sine theta. This 2D plane, therefore, is defined by the colatitude theta and the radial coordinate r, making theta the polar angle. And that's why we list theta second, because it is the polar angle. Now let's find the displacement vector in terms of the unit vectors. To do this, we first want to define the coordinates x, y, and z in terms of r, theta, and phi. X is just going to be r sine theta cosine phi, y is going to be r sine theta sine phi, and z is going to be r cosine theta. We can then invert these coordinates to find r, theta, and phi. You should look at the coordinate system and make sure that you understand how to get all 6 of these coordinates. Using these coordinates, we can now define our unit vectors r hat, phi hat, and theta hat. R hat is of course defined by taking the displacement vector and dividing it by the magnitude. We know that the displacement vector is just r sine theta cosine phi x hat plus r sine theta sine phi y hat plus r cosine theta z hat. The r's drop out and we're just left with this expression. Notice again that the r unit vector depends on theta and phi, in addition to x hat, y hat, and z hat. And this makes sense because our unit vector is going to change as the theta and phi change for the point. Phi hat is going to be exactly the same as in polar coordinates, so it's going to be negative sine phi x hat plus cosine phi y hat. Now all we have to do is find theta hat. And the way that we're going to do this is we're going to use our knowledge that r hat, phi hat, and theta hat are all perpendicular to one another, and that theta hat points clockwise in the plane defined by the z-axis and the displacement vector. What I want you to do for a problem is to actually find theta hat and use the fact that it should be perpendicular to the other unit vectors to help you. You should have found that theta hat is equal to cosine theta cosine phi x hat plus cosine theta sine phi y hat minus sine theta z hat. If you didn't, go back and check your math. Using this information for theta hat, phi hat, and r hat. Now that we know theta hat, we can go back and define the displacement vector in spherical polar coordinates. I want you to do this as a problem. I want you to write down the displacement vector in spherical polar coordinates using the unit vector notation. You should have found that the displacement vector in spherical polar coordinates is just r hat. This makes sense because r is the magnitude along the displacement vector, and r hat is the direction of our displacement vector. To make sure that you understand how to define the displacement vector in spherical polar coordinates, let's do a couple more problems. In the first problem, I want you to define the displacement vector to the Cartesian point 3, 4, 12 in spherical polar coordinates, using both the parenthetical notation and the unit vector notation. To find the answer, you should have calculated r as 13 and rho as 5. The colatitude theta will be given by the tangent of rho over z, while the azimuthal angle phi will be given by the tangent of y over x. Therefore, the parenthetical notation should be 13, tan inverse 5 over 12, tan inverse 4 over 3. And in terms of the unit vectors, it should be 13 r hat. Let's go ahead and do another problem. In this problem, I want you to take these parametric expressions for x, y, and z and find the displacement vector in spherical polar coordinates. In terms of the unit vector, you should have gotten square root 2 times t times r hat. And for the parenthetical notation, you should have gotten square root 2 times t, pi fourths, tan inverse of cotangent of 2t. If you were able to get the correct answers for this problem, good job. If not, you should read pages 134 to 135 in Taylor and do problem 4.40.
We've now talked about the three non-Cartesian coordinate systems of interest: polar coordinates, cylindrical polar coordinates, and spherical polar coordinates. Probably the different symbols are bouncing around in your head, but I want you to take a step further and compute the time derivative in each of these systems.
Our second learning goal is to calculate the time derivative. First, let's look at the time derivative in Cartesian coordinates to familiarize ourselves. The displacement vector is given by xx hat plus yy hat plus zz hat. To take the derivative of the displacement vector, we need to use the product rule on each of the terms. Therefore, we'll get both a dx over dt x hat term and an x plus dx hat over dt term. We'll do this for each term in our displacement vector. Since dx hat dt, dy hat dt, and dz hat dt are all 0, these terms drop out and we're just left with the dx dt x hat plus dy dt y hat plus dz dt z hat. This is because x hat and y hat and z hat are constant in time. They always point in the same direction. The second derivative of the displacement vector is then just going to be the second derivative of x with respect to t times x hat plus the second derivative of y with respect to t times y hat plus the second derivative of z with respect to t times z hat. Again, these dy hat dt terms drop out. In polar coordinates, things are going to be a little bit different. In polar coordinates, we know that our displacement vector is just r hat. So when we go ahead and we take the derivative of the displacement vector, we find again that dr dt r hat plus r times dr hat dt. But unlike dx hat dt, dr hat dt is not 0 because r hat is not fixed in time. Remember, it depends on phi, and so if phi is changing in time, r hat changes in time as well. Explicitly, r hat is equal to cosine phi x hat plus sine phi y hat. Therefore, when we take the time derivative of r hat with respect to t, we get negative sine phi d phi dt x hat plus cosine phi d phi dt y hat. But if we look at this negative sine phi x hat plus cosine phi y hat is really just phi hat. So the derivative of r hat with respect to t is just d phi dt phi hat. We can go ahead and plug that back in, and we get that dr dt r hat plus r times d phi dt phi hat. Hey, this is exactly what we got for the velocity in the introduction.
In the introduction, you might have been dubious of this extra r in the phi hat term. But now we can see from the calculation that this extra r arises because the r hat vector is dependent on phi. Let's look at it another way.
That other way is to look at what a small infinitesimal change in the displacement vector would look like. There could be a change in the radial vector, this would be dr, or there could be a change in the azimuthal angle phi. This change would correspond to an arc of r d phi. When we calculate the velocity, we do not actually want the derivative of the angle. We want the derivative of this arc length. So of course we end up with an r in the phi hat term, because we're going to get drr hat plus rd phi hat. Let's do some more problems to make sure that you understand what's happening. In this problem, I want you to find the acceleration vector in polar coordinates. To do this, you need to find what d phi hat dt equals. To find the acceleration vector, we're just going to take the derivative of the velocity vector. If we do that, we come up with these 5 terms. And we see some terms have a d phi hat dt in it. So we're going to need to find d phi hat dt. We've already found dr hat dt, so we can already plug that one in. But we still need to find this d phi hat dt. Phi hat, remember, is just going to be negative sine phi x hat plus cosine phi y hat. So when we go ahead and we take the derivative, we're going to get this following expression. Turns out that this simplifies to negative d phi dt r hat. So we can go ahead and plug that back into our equation. When we do that, we get the following 5 terms. Simplifying, we find these 4 terms. There's 2 terms in the r hat direction and 2 terms in the phi hat direction. This looks kind of messy, but if we look at each term individually, it becomes a little bit more clear. The first term here is just a regular radial acceleration, the second derivative of r with respect to t. The last term here is just the tangential acceleration. In introductory physics, you probably called this r alpha. Maybe it's coming back now. These other 2 terms are a little bit more difficult. This one here, you probably recognize as r omega squared, and this one is the centripetal acceleration. This third term here is called the Coriolis acceleration, and it isn't talked about much in introductory physics because generally in introductory physics, the radius of whatever you're looking at is constant. So this term generally falls out. Let's do another problem. In this problem, I want you to take these following expressions and find the velocity vector in polar coordinates. The first thing that you're going to want to do is take these expressions and plug them into our expression for the velocity vector. If we find dr dt and d phi dt and plug them in, we get this equation, which looks sort of messy. Go ahead and write this down and make sure that you've got the exact same equation that I've got here. Let's do one more problem. This time I want you to find the expression for the velocity vector in cylindrical polar coordinates and in spherical polar coordinates. For cylindrical polar coordinates, you should have found a velocity vector that's very similar to the one in polar coordinates. You should have gotten d rho dt rho hat plus rho d phi dt phi hat plus dz dt z hat. For spherical polar coordinates, the velocity vector starts out pretty similar to the velocity vector in polar coordinates. Again, you've got dr dt r hat plus r d theta dt theta hat. Now remember, theta is that polar angle. This last term is a little bit more difficult to understand. We've got r sine theta d phi dt phi hat. But remember, this r sine theta is really rho. And in cylindrical polar coordinates, this is rho d phi dt. So really, these terms are completely equivalent. If you were able to obtain these 2 solutions, then good job. If not, you should try and calculate the acceleration vectors for cylindrical polar coordinates and spherical polar coordinates on your own, because this will provide some good practice.
I'd like to move on now to calculating spatial integrals. But before we do, I'd like to leave you with one last thought. We've seen that there are these extra factors of r or r sine theta in the time derivatives for the angles. We know that they must be there so that the dimensional analysis is correct. We've also mathematically proven that they must be there because the unit vectors depend on the angles. But why are they there really? Why physically does the velocity have a term r sine theta instead of something else? To see that, we need to talk about the volume element. And luckily, we're going to do that when we talk about calculating spatial integrals.
Our third goal is to calculate the spatial integral. To calculate a spatial integral, we need to define the volume element. Cartesian coordinates, the volume element is going to be dv. It's going to be equal to dx, dy, dz. That is, if we went up here and we looked at an infinitesimal volume, it would be a cube. You'd have one length, dx, another length, dy, and the third length, dz. In non-Cartesian coordinate systems, dv is not actually a cube, and this may be a little surprising. To see what I mean, let's first reduce the dimensions by 1 and take a look at polar coordinates. To see what I mean, let's first reduce the dimensions by 1 and look at both Cartesian and polar coordinates. In two-dimensional Cartesian coordinates, the area element is just going to be dx times dy. That is, an infinitesimal displacement dx times an infinitesimal displacement dy here will make a square. In polar coordinates, the area element is going to be dr times r d phi. That is, that if we moved a little bit in the radial direction, we would move a distance dr, but if we moved slightly, swept out a larger angle, d phi, we would move a distance r d phi. This area element is not a square. It actually looks like the section of a washer. Using this information, we can now find what the volume element looks like in either cylindrical polar coordinates or spherical polar coordinates. In cylindrical polar coordinates, the volume element is going to be d rho times dz times rho d phi. Because if we sweep out small element of phi, we're going to actually sweep out an arc of rho d phi. This volume element is not a cube. It actually looks like the section of a 3D washer. In spherical polar coordinates, again we do not get a cube. Our volume element is again going to be dr times r d theta times r sine theta d phi. That is, this arc here is going to be rho d phi, where rho is equal to r sine theta. The distance here, if we move just a little bit in theta, is going to be r d theta, and if we move a little bit in r, it's going to be dr. So basically what we've done for all of these coordinate systems, Cartesian, polar, spherical polar, and cylindrical polar, is that we've looked at the graph in order to figure out what the volume element is. However, there's a mathematical way to determine this new volume element that just requires the determinant of a matrix of partial derivatives. This determinant is called the Jacobian, or J here. In order to find the volume element, we'll just look up J and multiply it by our three differentials, dw1, dw2, and dw3. For example, let's say that we want to find the volume element in spherical polar coordinates. We look up the Jacobian and we find that it's r squared sine theta, and then we multiply it by dr, d theta, and d phi. This is a very simple way of figuring out what the volume element is without looking at the graphical representation. Having defined this volume element, the only other thing we need in order to do a spatial integral is to define the range of integration for our r, theta, and phi. Now that we've defined this volume element, the only thing that we need to define is the range of integration to do a spatial integral. The range of integration for our Cartesian coordinates x, y, and z should be negative infinity to infinity. For our radial coordinates like r and rho, they'll typically have a range of 0 to infinity, with most of the time you'll integrate from 0 to a particular radius. Our coordinate phi will have a range of 0 to 2 pi, and our coordinate theta will have a range of 0 to pi. A lot of the time, students forget that the co-latitude has a range of 0 to pi. They think it has a range of 0 to 2 pi. But really, once you go past pi, you start double counting the angles. So for example, an inclination of 3 pi halves is just the same as pi halves from the z-axis. Now that we've defined the range of integration, let's go ahead and calculate a spatial integral. For this first problem, I want you to find the expression for the area of a circle by using your spatial integral. What we're going to do is I'm going to set up the integral for you, where the area of the circle is just going to be the integral of r d phi dr. We're going to integrate d phi from 0 to 2 pi, and we're going to integrate dr from 0 to r. Go ahead and solve for the area of a circle. You should have found that the area of a circle is equal to pi times big R squared. To do this integral, you could have just separated the r terms from the phi terms and then solved. Let's do another problem where I actually let you set up the integral and solve it. I want you to prove that the expression for a volume of a cylinder is pi big R squared times L by using a spatial integral. Set up this integral and solve. To set up the integral, you're going to want to set up a triple integral over d phi, d rho, and dz. Again, we'll need this rho in here because of the Jacobian. And we're going to set the range of integration from d phi from 0 to 2 pi. For d rho, it's going to be from 0 to r. And from dz, it's going to be from 0 to L. Could have also done negative L halves to L halves, or some variation thereof. You'll get the same answer. Then we can solve this triple integral by just separating each of the terms. And you'll find that you get pi times big R squared times L, which is the familiar volume of a cylinder. Let's do one more. This time I want you to prove that the expression for the volume of a sphere is 4 pi r cubed divided by 3 by using a spatial integral. Here again, you need to set up a triple integral. You're going to use the Jacobian r squared sine theta, and you'll need this element dr, d theta, and d phi. Dr will go from 0 to big R, d theta will go from 0 to pi, and d phi will go from 0 to 2 pi. When you solve this integral, you should find that you get 4/3 pi times big R cubed, or the familiar equation for the volume of a sphere. Hopefully you're getting the hang of using the volume element in non-Cartesian coordinates. If not, why don't you try to find the center of mass of a sphere or a cylinder using a spatial integral. Another great problem is to find the center of mass of a solid cone. The answer is in your book in section 3.3 if you'd like to do this problem. Conclusion. Here we've learned about working and deriving in non-Cartesian coordinate systems. We've talked about all of our learning goals. The first learning goal was to define the displacement vector in non-Cartesian coordinate systems such as polar coordinates, spherical polar coordinates, and cylindrical polar coordinates. We've calculated time derivatives in these non-Cartesian coordinate systems, and we've calculated spatial integrals in these non-Cartesian coordinate systems. So you should have a lot of good practice with doing these things.
But why did we do all of this? Aren't we supposed to be learning physics in this course and not math? Really, our goal during this course will be to describe the dynamics of objects. We want to do that using the simplest form that we can, and many of the times this will be using non-Cartesian coordinates. Being able to define physical variables in these coordinates and both derive and integrate these variables will be paramount for describing the physics behind the movement. If we want to look at motion in a rotating frame, for example, it would be really nice to define the angle of rotation instead of using a complex expression in Cartesian coordinates. Later, when we get to Lagrangian mechanics, we'll look at even more flexible coordinates than the ones I've described. So having this background will be very valuable. That's it.